Hi everyone! In this video, we'll take a look at two examples to calculate the molarity of an unknown using titration data. In the first example, the titrant is the unknown, and in the second example, the analyte is the unknown. Both situations will follow the same strategy to calculate the molarity. First, we calculate the moles of the known reactant using its volume and molarity. The second step is to apply stoichiometry, that mole-to-mole ratio, to relate the two reactants from the balanced equation. And the third step is to calculate the molarity of our unknown from the moles that we just calculated from stoichiometry and the volume of the unknown. There are a few things to remember with these types of calculations. First, never use the dilution equation to solve these problems. These are not dilution problems because we're not diluting one substance to a different concentration. They are solution stoichiometry problems which relate two substances via balanced chemical equation. The next thing is, we do want to make sure we include the stoichiometry step even if the mole-to-mole ratio is 1:1. This is to ensure that the units cancel correctly. And finally, we do want to be careful to align the substance with its volume. What I mean by this is when you're calculating the moles or molarity of the titrant, use the titrant volume as needed in that calculation. If you're calculating the moles or molarity of the analyte, use the analyte volume. This brings us to our first example. So in this example, we know the information about the acid, and so we can calculate the moles of this reactant. The second step will be to relate the moles of HCl that we just calculated to the moles of NaOH. So we're relating our known to our unknown. And we use the stoichiometry of the balanced equation. And the third step is to use the volume of the NaOH and the moles that we just calculated to calculate molarity. So like all types of problems, we start with what we're given. Now it doesn't matter here if you apply the volume first or the molarity first of the HCl, as long as things are set up correctly so the units will cancel. The other thing is we need to make sure that our volumes are in liters. So I'll go ahead and just write that out first so we have it. So our 25 mils is going to be 0.02500 liters. Make sure to include all significant figures. And then our second volume is 0.03381 liters. And the last thing we need to do before we actually start working through the calculation is to write down our balanced equation. So our balanced equation is HCl plus NaOH going to NaCl plus H2O. Okay, now we're ready to begin. So we'll start with the volume, 0.02500, and this is liters of HCl solution. Then we're going to multiply that by the HCl molarity, expanding those units of molarity into a clear numerator and clear denominator. So at the top we have 0.0753 moles of HCl divided by liters of solution. So liters of solution will cancel, and at this point we have moles of HCl. Now we'll apply our stoichiometry step. So we have 1 mole of NaOH at the top and 1 mole of HCl at the bottom. Moles of HCl will cancel, and we're now at moles of NaOH. So there are two ways you can finish this calculation. you can stop here, calculate moles of NaOH, and then divide by its liters, or we can apply it as just our final step as 1 over liters, so 0.03381 liters of solution. So we're left with moles over liters, and that will be molarity. Let's take a look at our sig figs so we know how far we need to round. Our initial volume has 4 sig figs. Our HCl molarity has 3 sig figs. Stoichiometry is always exact. And our NaOH volume has 4 sig figs. So when we do the calculation, we will round to the fewest number, which is 3 sig figs. So doing the math, 0.02500 times 0.0753 divided by 0.03381, rounded to 3 sig figs, gives us 0.0557. And that's molar or molarity NaOH. In our second example, we're setting out to calculate the molarity of an unknown acetic acid solution, and in this case, the titrant is known. So we identify that information. So we have our known NaOH. So notice the similarity with how we identified the information here as compared to the previous example. It's the same idea. So this is where we'll calculate moles of the reactant that we know. The second step will be to relate moles of the NaOH, which is known, to the moles of acetic acid using the stoichiometry mole-to-mole ratio. And then the third step is over here. Now we have the moles of acetic acid and the volume of that acetic acid, and that allows us to calculate molarity. So for the balanced equation, we have acetic acid being titrated with NaOH to form sodium acetate and water. So this is also a one-to-one stoichiometry, but we still want to be in the habit of identifying that chemical equation and then writing down that stoichiometry step. Just like the last example, our volumes are given in milliliters, but we'll want to convert them to liters to do the calculation. So the volume of the NaOH will give us 0.01641 liters, and the volume of our acetic acid is 0.00500 liters. Make sure to include all of the zeros, both the leading zeros and the trailing zeros that account for our sig figs. So to start this calculation, we have 0.01641 liters of solution. We then apply the molarity of the NaOH, 0.0994 moles of NaOH over liters of solution. So liters of solution will cancel. Next is our stoichiometry step. So we have 1 mole NaOH at the bottom of our conversion factor and 1 mole acetic acid at the top. And then this last step will apply in a similar way to our previous example, 1 over the acetic acid volume, which is 0.00500 0.500 liters of solution. Taking a look at our sig figs before we do the calculation, we have 4 sig figs for our volume, 3 for our molarity, stoic is always exact, and 3 sig figs for our other volume. So we'll be rounding this result to 3 sig figs. Doing the calculation, 0.01641 times 0.0994 divided by 0.00500, rounded to 3 sig figs, gives us 0.326 molar acetic acid.